We're asked to draw a free body diagram for a jumper jumping upward and accelerating at 6 meters per second squared, while his feet, of course, are still in contact with the floor. So, free body diagram, here's our jumper. Remember, any object, any point-like object in a free body diagram is represented by a point. We're going to regard the jumper as a point, and we're just going to draw the forces on the jumper. Now, two things we know. We know that gravity acts, well, more than that. We know that gravity acts downward, and a normal force from the floor acts upward. Okay, the jumper pushes his or her feet down to the floor, into the floor, and the floor, which is already supporting the jumper's weight, has to exert additional force equal and opposite to the extra downward force that's being exerted on it, and that's called the normal force exerted by the floor, and that's going to be in the upward direction. It's going to be directed upward. Okay, so we're going to have a gravitational force down, a normal force upward, and since the jumper is accelerating upward, the normal force has to be greater than the gravitational force. Remember again, when the jumper is standing on the floor is exerting a force equal and opposite to the gravitational force. When the jumper pushes down on the floor has to exert that much force plus extra, so it does have to be longer than the gravitational force vector. Then the normal force vector will be longer than the gravitational force vector. Now, I've exaggerated how long that should be compared to this one, but we can make some adjustments. Okay, now we know that the picture looks like this, and we know that the net force is mass times acceleration. In this situation, you're given that the mass of the jumper, I think, is 80 kilograms, and the upward acceleration is 6 meters per second squared. So we have an upward acceleration. The net force, therefore, is upward. And again, that's this. And this has to be this plus this. Okay, because the net force is the sum of all the forces. So the net force will be this force added to this force. Well, let's see what we know. The net force from the given information is 480 newtons upward, and that's very easily found. We multiply the mass by the given mass by the given acceleration. We also know how much force gravity exerts. It's going to be a downward force of 80 kilograms times 9.8 meters per second squared, about 800 newtons downward, and I'm using just kind of round numbers here. Okay. The net force is a gravitational force plus the normal force. If we let upward be the positive direction, well, the net force is your plus 480 newtons obtained by your mass and acceleration. Your gravitational force is the negative 800 newtons. Having decided that positive is going to be up for this problem, our downward force, of course, then becomes negative. And that's added to F normal. Okay, so gravitational force and the normal force add up to the 480 Newton net force. You really want to write out this equation. People are making all kinds of mistakes by using intuition and getting things backwards. If you don't write out this equation, you're at high risk for screwing something up. Okay, so we write out the equation and we solve for F normal, adding 800 newtons to both sides. We get F normal 480 newtons plus 800 newtons equals 1280 newtons, and that's the force we were trying to find. Now, the acceleration here has magnitude 6 meters per second squared, giving us a force that I expressed with a vector that's about this long. It's not much different than the length of the gravitational force vector, which ought to be somewhat longer to be in the same scale with this one, and also with the normal force. So I'm going to just kind of extend that gravitational force vector down to about here, so it's in the right proportion with this vector. Remember, you have an acceleration on a mass of 9.8 meters per second here, and on the same mass of 6 meters per second squared here. I say 980.8 meters per second squared. Any case, the gravitational force vector is more than half again as big as this vector. They're in opposite directions, but their sizes are dictated by the magnitudes of those accelerations on the same mass in both cases, of course. Okay, now the picture looks better. This force is in better proportion with this, and if we add this force to this force, we get something pretty close to this force. Maybe this normal force should be a little higher now as well. You can work out the proportions. You do want to try to make these things in about the right proportions, just to reinforce your intuition, your understanding of what's going on. The other thing I'll say is that we got the normal force, we got the gravitational force, we got the net force. Those things make what I call a triad, a diagram that indicates that if you know any two of these, you can find the third. And the way we find the third is by using this equation, which, again, I'll repeat, we always ought to write out, and we always need to be very careful about the signs of all our quantities. Declare a positive direction. All quantities have signs then that are determined by their relationship to that positive direction.